Sound people, welcome back to my little series. This is episode 3. We're going to be taking a little break from the board for right now because I want to go over a series of topics that in my crew we call Sound Day. Sound Day, and every time I refer to it, it's in all caps with several exclamation marks after it to try to make it sound as fun as possible. And it's a lot more interesting than referring to it as an explanation of sound from a physics and psychology perspective, because that's what it really is. The first meeting, after everybody has learned each other's names for every show, is Sound Day. This is a day where I go over with the sound members basically what sound is, and everything about sound from a not strictly theater's perspective, just in general. That's why I have a whiteboard with me here to help draw out some of the concepts for you. And I really hope that Sound Day is a tradition that never dies, because I genuinely think it's really good for the sound members to have an understanding of how this plays into the bigger picture of physics while they're creating sound effects and doing stuff. And also it helps with making sound effects, a lot of the frequency stuff. So, what is sound? Well, there's two definitions. There's the physics definition, which is that sound is just whenever literally anything is vibrating. Because this is pretty common knowledge, if you hit something and it makes a sound, that sound comes from two things. When you hit something, the air vibrates in a certain way, and then also the thing that you hit vibrates, and that causes the air to vibrate, and those vibrations hit your ear. Your ear is a very special technical tool that is trained to detect differences in air pressure and the vibrations in the air that is created by the sound of hitting things, snapping, things like that. They create those little differences in air pressure that your ears hear, but then creates this perceptual experience that is sound from a psychology definition. Understanding how these two definitions are different is pretty important. Physics is specifically the vibrations and that kind of thing, but psychology is how we perceive sound. And we're going to get more into the psychology definition later when we talk about the difference between white and pink noise. But for right now, I want to talk about just the physics definition. When you snap, it is causing the air to vibrate, and those vibrations are hitting your ear. However, when you hit something, if it's like a tuning fork or something like that, which is perfectly designed for this, that will start to vibrate, and that will shake the air around it. So, what are the parts of a sound wave? There are two types of waves. There are transverse waves, which are the waves that you're kind of used to, that look like this. But then there are also longitudinal waves. This is what a transverse wave looks like, where it's just the pretty standard wavy wave. This is a longitudinal wave. It is a wave that is created by particles that get closer together at one point and then are farther away. So, naturally, if this was turned into a transverse wave, it would look something like that. If this were turned into longitudinal, it would be that is my best impression of replicating this as a longitudinal wave, where it gets a lot closer at the peaks, and then the dots get really far away from each other at the troughs. Sound waves are longitudinal. Because sound waves are air vibrating and these vibrations hitting each other, sound waves are longitudinal, not transverse. However, because studying longitudinal waves is a lot harder than studying transverse waves, we're just going to treat it like it's a transverse wave for now. We're going to pretend that it is. So, let's express a sound wave like this. So, we are going to have the center line here. The parts of a wave. You go over this in basic physics, but right now I want to cover it because there's an interesting thing to learn. This distance right here, this is the amplitude of a wave. Amplitude is not the total height from the peak to the trough. A peak is where it peaks, a trough is the opposite of a peak. The amplitude is half of that, because the amplitude is the height from a peak or a trough to the center. This amplitude will always be the same as the thing here. In sound waves, if you zoom in enough to the point where you can see the sound wave like this, the amplitudes will always look the exact same. You're never going to have a wave that looks like that. You're not. You're always going to have waves that look like this, where the amplitudes are going to be consistently the same. Cool. That's amplitude. Wavelength. The distance from here to not there, there. Oh god, that was terrible. The distance from here to here is wavelength. The length that the wave goes before it repeats. If you take one section of it, that's one chunk. That's one wavelength of the wave. There's also the frequency of a wave. Frequency is, if you imagine the wave, imagine I took this thing and it was this little marker, and you could see the waves on this little marker. Sound waves, like light waves, travel. And if you take one point, the frequency is how many times a wavelength passes that point in 1 second. So if this was one wavelength, and it took 0, 1 second to pass through a point in space, then it has a frequency of 1 hertz. Hertz is number of times per second that a wavelength passes through a point. So, you might also know frequency as what causes sound to sound like this. You know that things that sound like this are low frequency. And you know that things that sound like this are high frequency. You might know that. Also, low notes, high notes, are different because low frequency, high frequency. What causes that? Well, that is what we're going to spend a lot of time covering here. That is the same definition of frequency. What causes sound waves that pass through that point slowly are going to sound like this. And sound waves that travel through that point pretty fast are going to sound more like this. That is frequency. The speed of sound is a constant. The speed of sound is a constant. The speed of sound is a constant. That is very important to remember. And the speed of sound is, in fact... Let me get the value in meters per second, because that is metric. 343 meters per second. Speed of sound, hold on, C equals 343 meters per second. Why is the speed of sound being a constant so important? I realize that's probably going to be reversed. I can flip it. If I can't, I'm sorry. Because that means that the speed of sound is the same no matter what the frequency is. Wait a minute, Gus. How can the speed of sound be the same if this one little wavelength going slowly passing through the point is a low frequency, and going faster than a point is a high frequency? How can that be possible if the speed of sound is always the same? Wavelength. The speed of sound is a constant no matter what the frequency is, which means that wavelength and frequency are basically the exact same thing for sound waves. That is important to remember. It means that because no matter what frequency a sound wave is, it's always going the same speed, that what is going to affect the frequency of something is the wavelength. So like a sound wave that's really long is going to be moving the same speed, so it's going to have a lower frequency passing that point than one that has a lot of peaks and troughs. Cool, but everything goes the same speed. And everything goes a speed that we know is 343 meters per second. So, as a fun fact, we can use that. We know that the wavelength, yes, the equation is lambda equals velocity over frequency. This is a physics equation. Wavelength equals velocity over frequency. We're talking sound here, so this value is always going to be 343, which allows us to do some pretty fun stuff. If I use a spectrograph to play a musical note, I'll just sing for right now. Oh, shoot, but I don't have a microphone set up. 1 second, fam. Hello, testing. I don't need you, I just need you. I have a microphone now. So what this microphone is going to be for is I can sing into Barry, and using the EQ visualizer, I can see the frequencies. I can see the frequencies of my voice as I'm talking right here. Let me try to get an isolated note for you. Change. You can see the frequency of that note. Change. That is about 200 and that's 300, so that's about 250 hertz. Okay. We have a frequency. That note right there. That note is 250 hertz. Which means that we know what the wavelength is. All we need to know is the frequency, and we know the wavelength. All we need to know is the wavelength to know the frequency. And so we can plug this into a calculator. 343 divided by 250. That's going to be around 1-ish, maybe a little more. My phone is being used to record this, so I can't just do that. Oh, I have a computer right here. Hold on. 343 divided by 250 is the meters. Meters to feet. 1.372 meters to feet. Because that's just easier to visualize. Okay. So, that note, change, that note is exactly this big. The wavelength of that note is this big. That note has this much wave. That is the exact wavelength. The air molecules are vibrating exactly this much. Not exactly because I'm approximating, but roughly this much. Isn't that crazy? Isn't that so cool that using math, we can play a musical note, I can sing, and we can find the wavelength using math? Like, we can find the distance of which the air molecules are vibrating. I like, sing a note, and I can just, this big. That's wild. You can do the exact same thing in reverse. You can find the length of an object. And plug that in as the wavelength in that equation, find the frequency, go to some little online thing, play a frequency with that exact same, frequency. That was redundant. And that thing will start vibrating like frick, because you're playing a frequency whose wavelength perfectly corresponds with that object. Cool stuff happens. That's a bunch of stuff that you can do with sound from a physics perspective. Let's talk about sound from more of a sensational perspective. We have all these concepts in our head about like what sound sounds like, and how different things affect different sounds. For example, if you hear me talking right now, it sounds like this. But if there was a wall between us and you were like eavesdropping on me from another room, you might hear me like talking like this a little bit, but why would I sound like a little lower pitched? Why would I sound lower pitched? It is because sound doesn't just travel through air. It can travel through water, it can travel through walls, it can travel through anything. But the thing is, sometimes what sound travels through affects the way it comes out. Like if you have a wall, the high frequencies that hit the wall are going to bounce off. The low frequencies that hit the wall are likely going to pass through. Which means that what you're hearing of somebody isn't just their voice pitched down, it's just only the low parts of their voice and not any of the high parts. Because most of the high parts are bouncing off. So, that is why hearing somebody through a wall sounds lower pitched. Old-fashioned telephones. If you like do a little impression of somebody talking in an old-fashioned telephone, or like a radio announcer, or something like that, you will notice that your voice naturally gets higher pitched. Why is that? It's because that kind of technology, when converting sound waves into electrical waves, had to make sacrifices to the quality of the sound to make it travel. Namely, dropping many of the low frequencies. Meaning that when you're talking like this and you imitate this higher pitched voice, it's because that technology back in the day, like, what's the word I'm looking for? Specialized in high frequencies. So it sounded higher pitched. And that's what led to that phenomenon. When you're talking I can't do it. But when you're talking underwater, it sounds lower pitched because naturally water is thicker, more dense. It makes high frequencies are more likely to bounce off, low frequencies are more likely to pass through. Listening to something underwater, if you've ever seen like a movie clip of something where the camera like dips underwater and everything gets way lower frequency, That's why, because water affects it. Cool. What else? Oh, let's talk about the cool thing about frequencies. I did that thing where I played a note and you got the wavelength, which is 4.5 feet. High frequencies, the human hearing range, I should start there, is, I believe, 2 to 20,000 kilohertz? Yeah, 20 hertz to 20,000 hertz. That is the human hearing range. 20 hertz is probably around the lowest note you can hear. 20,000 hertz is the highest note you can hear, on average. 20 is the size of several football fields. Oh god, I'm so American. It is massive. A 20 hertz wavelength, plug that into our little equation, that's 343. F is really small. The frequency is real. Oh, wait, shoot. 20 hertz is the frequency. Okay, well, it's still really small. Much less small, but it's really small. But a high frequency note, 20,000. Oh, wait, I got it the other way around. That's why. High frequency, that's going to be extremely small. The wavelength is extremely small. The wavelength is literally, plug that into a calculator, 343 over 20,000. And we don't need to. But that's so infinitesimally small, and that is how long a wavelength is for a high note. Or, well, the highest notes. But high notes are really small, and big notes are pretty long. 343 over 20 meters long, actually. But how can... The point I'm trying to make here is that the difference between that distance for 20,000 and the distance for 20 hertz, that is only achievable because frequency does not scale linearly. It is not like 20, 30, 40, 50, 60, 70, all the way up to 20,000. It is logarithmic. You will also notice that the same thing is true with decibels. What I mean by logarithmic is that the scale doesn't just go like 0, 5, 10, 15, 20, 25, 30. It's not even. This goes from 0, suddenly before you even know it, you're at 60, and then you're at negative infinity. I don't know how well that read, but how well you can see the decibel levels there. Most things in sound are logarithmic as opposed to linear. So that means that instead of the graph looking like this, the graph looks like that. Because that's logarithmic, or exponential, synonyms. Logarithmic is technically the opposite of exponential, but you get the point. Anyways. That means that you can do some cool stuff with that. Sorry, my energy is gone. Nar! Where did it go? Where was I? Okay, the point I'm trying to make here is the way that is achievable, we can go from 20,000 hertz being such a small distance to 20 hertz being such a massive distance, is because sound scales logarithmically or exponentially rather than linearly. That means that the amount of distance for 20,000 hertz is this small, and when you get... And I'm just going to, imagine that this is the distance, and as the frequency is going up, it gets, smaller, or, well, it gets bigger. It gets bigger pretty slowly, then it starts getting bigger faster, and then it starts getting bigger faster, and then, whoa, it's really big really fast. It's exponential. This means that if you were trying to create a device, let's say we're trying to create some weird device where there was a little button you could hit, and it played a musical note of a frequency. Let's have this one be the lowest note possible. Let's create another button here, and another button here, and more buttons. We're just going to create a ton of buttons. And all of these buttons, when you press it, plays a musical note. This is a low note, this is the next lowest note, and then highest note. And let's have it be so that using the psychology definition of sound, we hear all of these notes in a musical scale, or the notes increase linearly. However, when our perception of the notes increases linearly, by the physics definition, the actual wavelength is increasing exponentially. So, how could we have these buttons play a musical note? Well, the easiest way to vibrate a string. So we're going to attach them to a string that is going to vibrate. And because the string is vibrating, it is going to vibrate the air in a wavelength equal to the length of the string. It's that simple. So this one's going to have to be really long. The next note is going to be not as long. But wait. Oh, shoot. This isn't going to look like this. I'm doing my best to draw this. It's not going to look like that, where there's just this straight, even line, because wavelength doesn't increase linearly. It would look like that if that were the case, but because it doesn't, that means that what the lines actually will look like is more like this. Hold on, let me, oh yeah, there we go. Oh, I dropped it off too quickly. Alright, screw these for right now. It's gonna look like a curve. And whoa, I just invented a piano. Oh man! But the point here is that that's why the backs of pianos look curved. Now, also, they usually have that, like that little sinusoidal thing. Oh my god, I suck at drawing. But that's why the backs of pianos are curved. Is because the length of the string that goes to the back, to play musical notes that increase linearly in how we perceive them, the actual length of the string has to increase or decrease, depending on the way you're looking at it, exponentially. That is one of the key principles of sounding, is that is how frequencies work. Another cool thing about frequency. We were talking a little bit earlier about how old-fashioned telephones make you higher pitched, being underwater makes you lower pitched. By the way, if you're ever doing a scene in a play where characters are underwater, you're going to want to EQ that so that it's lower pitched. If they're ever talking on old-fashioned radios like Grantland and Rice and Failure, which we just did, you're going to want to EQ that so that it's a little higher pitched. Cool. Also, let's do a little experiment, right? The speed of sound is a constant. But wait, Gus, how come when I'm using an audio editing thing, it gives me the option to slow something down or speed it up? How does that work? Because obviously the speed of sound is a constant. It can't make the sound waves go faster. Well, let's try this. I'm going to say the word biscuits. Oh god, my voice is not going to be good for this. But I'm going to start saying word biscuits normally, like this. Biscuits. 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 And I'm going to slow down. Biscuits. 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 I was doing my best to imitate, like, slowing down, but you could hear that something that my brain was unconsciously doing is, as I was saying that, I was getting lower and lower pitched. Hey, why is that? It's almost like slowing down a wavelength is literally just stretching it out and playing it at the same thing. And hey, what happens when you stretch out a wavelength? The frequency is lower because the wavelength is longer. So slowing sound down is really just making it lower pitched. And the exact same thing. If I say biscuits, 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 you get the point. If I speed up, then that's going to make it higher pitched because I'm compressing that wave into such a small distance that it's making the frequency go higher exponentially. So slowing down is the same as pitching down. And speeding up is the same as upping the pitch. Essential sound knowledge for you. Cool. Now, this is where I would do some fun little games. I would have them improv a scene where they are using a telephone, trying to talk to somebody who's underwater. Guess that frequency. Oh, we've talked a lot about frequency. Let's talk about that other part of a wave. Amplitude. What does amplitude control? Well, volume. It controls volume. I was going to do like some fancy little joke for that, but no, it just controls volume. A wave that sounds like this is going to be a lot louder than a wave that sounds like this. even if they have the exact same frequency, amplitude controls how loud a wave is. Sorry, Ed. So that's what amplitude is. But also, volume's pretty weird. And it's hard to objectify volume, because volume also has the physics definition of just how big the amplitude is, but also the psychology definition of how loud a wave is to you, how loud a sound is to you. But, you know that old-timey thing where if a tree falls in the forest and no one is around to hear it, does it make a sound? That question is getting at the perceptual psychology of sound. I'm going to ask, if a tree falls in the forest, how loud is it? Because nobody's around to hear it. If somebody, while that tree is falling, is standing right here and they hear that tree fall over, that's pretty dang loud. But if the tree's falling over here and somebody's like all the way over here when it falls down, they're not going to think it's that loud. They're going to hear it, but it's going to be pretty quiet. So if you ask those two people how loud was the tree, they're going to give completely different responses. Similarly, if you took somebody with a really good sense of hearing versus somebody with a really bad sense of hearing, they're going to think it was a completely different decibel level. Decibel being like the unit for how loud something is. So perception of volume is just as important as the actual physics of it. And it's very important to account in doing sound for theater and editing sound. It's important to keep that in mind as you're choosing decibel levels. One interesting application of this is on the internet. Sound is completely like relative. Like if I have a YouTube video where somebody's playing the drums and the guitar, and the drums are this loud and the guitar is this loud, obviously that's going to sound pretty bad. So I want it to sound pretty good, so I'm going to turn up that guitar. Now it sounds pretty good. But also, this person who's editing this doesn't know, but that is ridiculously loud. But all they hear is maybe they have the volume on their computer all the way down, and they think this sounds good. Somebody else, another person editing a different video, has their volume all the way up? Yeah, all the way up. And they have the exact same situation where their drums are like this and their guitar is like this, but their solution is to turn their drums all the way down to match the guitar. So now, we have two people who think that the drums and the guitar sound the exact same, and they're right, but also they both upload this to like YouTube or whatever, and they run into the problem where this video is way quieter than this one, and it's because of that perceptual aspect of it. Sound, obviously it has a volume, like everything has a volume, but when you get to like the psychology of it, sound really doesn't have a volume unless you have something to compare that sound to. That's what mixing is. It's called mixing. It's not called, like, upping the volume fader. It's called mixing because you're adjusting the volume of everything in relative to everything else. If the drums are too loud, you can either turn the drums down or bring everything else up, and it's basically doing the same thing. That's what mixing is. Fun. Okay. We did the tree falls in the forest. I think that's about it. I think that's sound day. Obviously, if you're the chief, when you're teaching this to your crew, be way more expressive. Try to encapsulate the same amount of energy, because if you do it wrong, this lesson can be pretty boring. But if you're enthusiastic about it and you like show the kids like all these cool realizations like about how a lot of instruments work, and show how the idea of frequency and wavelength being the same thing according to the speed of sound being a constant, how that affects everything basically, like speeding up, slowing down, this lesson can be really cool and really fun, and you can incorporate so many little activities and lesson plans into it. Get creative. With that, I think this brings episode 3 of our little sound series to a close. Yeah, that was Sound Day. Should usually be the first meeting of every show if you're the chief. If you're the tech coordinator or running events, you don't really need to worry about this one. Should have said that at the start. Yeah. All right. Catch you on the flip side.